Okay. Hi, everyone. We're very happy to have Francesco here today to tell us about anomalies and gauging of U1 symmetries. Feel free to start.
Yes, okay. So thank you very much for the invitation. I'm very happy to give this talk. Of course, if you have questions or comments or criticism at any time, please do. Please shout if you have questions, because for me the camera is, I mean, I see you very small, so I might not see you. If you raise a hand, I don't see you. So please shout if you have a question.
Fair enough.
Yes, and so what I would like to do is to tell you about some recent work that I did with one of my students, Andrea Antinucci, who is moving to Oxford next year. By the way, can you see the pointer?
We can.
Yes.
Okay, very good. And so, yeah, so this will have to do with a description of symmetries and anomalies through something that is called Symmetry TFT. So this will be the topic. So more generally, the theme of this talk will be within the so-called generalized symmetries. So many of you might be familiar with this, but maybe not everybody. So this is essentially a new paradigm to describe symmetries in quantum field theory. And in this talk, I will work in Euclidean quantum field theory. And in this new paradigm, essentially, everything that is a topological de facto operator of any dimension in a quantum field theory should be regarded as some sort of symmetry. So what do I mean by that? So first of all, this new paradigm, of course, must encompass the old and well-established formulation of symmetry. So if we have some standard symmetry, some group G, and in this new paradigm, a standard symmetry is called a zero-form symmetry, for a reason that will be clear in a moment. Then in this new paradigm, essentially, we have some topological de facto operators. They are of codimension 1, so they are essentially like domain walls, like in this picture. There are as many as the elements of the group. So G is an element of the group, and for each element, there is a different defect. These defects will encode everything that we know about the symmetry in the standard terms. So in particular, we can take these defects. Now, what does it mean that these defects are topological? It means that if we compute some correlation function in this quantum field theory, and in this correlation function, usually we have some local operators. Now, we can also insert these defects, and we can freely move continuously these defects, and as long as we don't cross something else, the correlation functions do not change as we continuously deform the position of these defects. So in particular, if you have two parallel defects, we can fuse them, and then they look like a single defect. And the fusion of these defects precisely reproduces the group law, the product law of the group. So if I have UG and I fuse with UH, I get U corresponding to the element GH that reconstruct the multiplication law of the group. These operators also reproduce the action, for instance, on local operators, because we can take a local operator and now we can move it through one of these topological operators. Now there is a crossing, so something changes. However, the physics is, well, let's say that we keep fixed the local operator and then we move the topological operator. So once the topological operator is on the other side of the local operator, if we want the correlation function to remain invariant, we have to rotate the local operator. And of course, this transforms according to our representation. So we also reconstruct the standard concept that local operators transform in representations of the symmetry. And the statement of charge conservation in this new paradigm precisely corresponds to the fact that these defects are topological. So they can be deformed. In fact, take the standard case, very simple case of a U1 symmetry. Since it is a continuous symmetry, there is a current operator J. We can integrate the current. on a spatial slice, which in Euclidean signature is just a codimension 1 submanifold. This gives us the charge, which is Hermitian. And if we take the exponential, we obtain some unitary operator. This parameter alpha, in fact, takes value between 0 and 2 pi, precisely because the charge is quantized. So we can identify alpha with an element of the group. And the fact that the charge is conserved, sorry, that the current is conserved, implies that you can move this operator U and correlation function do not change. Besides, precisely when you cross a local operator, or you can use the word identity that relates correlation function of the current and the operator, and you precisely obtain the standard results that the operator is transformed with a phase, alpha, and Q is the charge of the operator. So this reproduces the standard facts about symmetry. However, it introduces, once again, this new paradigm introduces a lot of new structures. For instance, we can consider the effects of higher codimension, or if you want, lower dimension. And if the codimension is p plus 1, then we talk about a p-form symmetry. Why we do that? Well, because this p indicates the dimensionality of the extended operators that carry the charges under this symmetry. And how do we measure the charges? Well, if we have local operators, we put our codimension 1 surface around it, and we measure the charge which is inside. If we have a p-form symmetry, we do the same. So this black line is the extended operator. This blue line is the topological operator. And if we move it through the line, we pick up a phase, and this phase measures the charge of the operator. So we use standard braiding. Well, in fact, we can obtain much more. So for instance, we can have symmetries that act on other symmetries. If we were dealing with zero-form symmetry, we would just say that we have a non-Abelian group, right? If we have some elements of the symmetry that act on other elements. But here we might have elements of the symmetry that have different dimensionality, for instance, a zero-form symmetry and a p-form symmetry. So we can still distinguish the various elements. They do not form a non-Abelian group. They form something that is called an N group, for instance, a 2 group or a 3 group, and so on. And the basic example is here. So I already described what happens if a local operator goes through a topological operator, for instance, for a zero-form symmetry. Now, suppose that you have a line, like a Wilson line, and suppose that this topological operator is charge conjugation. Then also line will be transformed. For instance, a Wilson line in representation A, on the other side, will be a Wilson line in the conjugate, charge conjugate representation. So this surface can act on lines as well. And suppose that these lines are actually topological, so they represent some symmetry. For instance, if you are in Chern-Simons theory or Young-Mills Chern-Simons theory, then you have that some elements of the symmetry act on other elements. So you have this 2 group or higher group. There are also other effects related to these N groups that are represented by this picture, but let me not go there. So what else? Well, we can have the phenomenon that instead of having a group, so the symmetry, instead of being a group, can be a more general algebraic structure, for instance, a fusion algebra. So it might happen that when you take 2 elements and we fuse them, we don't just get a single element, but we get a sum of other elements. And you might be familiar with this, for instance, in 2-dimensional rational conformal field theory, the local operators, the primaries form a fusion algebra, and correspondingly also the Verlinde lines form a fusion algebra. So this is a generalization of the concept of group. In the standard fusion algebra in 2 dimensions, these n are integer coefficients. However, when we go to higher dimensions, we have a further generalization in which we might have fusion algebras in which these objects here are not numbers, but rather they are topological field theories. And so, in particular, depending on the submanifold that is wrapped by these operators U, you have to compute a partition function of the topological field theory n. And so depending on the topology of this submanifold, you get different numbers because you can get this partition function will correspond to different numbers. While, for instance, if you have a line, then it means that you have some topological quantum mechanics, and then the partition function of this quantum mechanics is just the dimension of a Hilbert space, and so for that reason, it's just an integer, non-negative number. But otherwise, it generalizes. Okay, so there is a lot of structure, and it turns out that a very convenient gadget that people have discovered in order to describe the structure of the symmetry and various properties of the symmetry, like, for instance, anomalies, representations, and so on and so forth, as I will describe, is something that has been called the Symmetry TFT, Symmetry Topological Field Theory. So let me describe what this is, and I can motivate it in different ways. So let me try to motivate it in my personal way. I mean, in a way that I find useful. Suppose that we have some theory, some quantum field theory that I will call TD. So this is some quantum field theory in D dimensions. And suppose that this theory has some discrete standard symmetry G, for instance, is a group, with some Toft anomaly. So we have been knowing for a long time that we can decide this anomaly in terms of, is there any question? Okay.
No questions, but you did sort of break up for a minute there, but it's all good. It's the connection's fine. So yep, please continue.
Okay, good. Yes, so it has been known for a long time that we can describe Toft anomalies by anomaly inflow. And in particular, we should think of this theory, the quantum field theory with a Toft anomaly, as living at the boundary of an invertible TQFT. This is also called, in condensed matter physics, this is called a symmetry protected topological phase, SPT phase for short. In mathematical terms, this is called the invertible TQFT. And so this invertible TQFT is a topological quantum field theory that has a single state on any spatial manifold. The partition function is always a number of modulus 1, so it's just a phase. And this phase precisely describes the Toft anomaly. So we can call this, if we want, an anomaly TFT. So now, suppose that part of this symmetry, for instance, some subgroup H is anomaly free, then we can gauge it, and we can obtain a new theory. Let me call it TD mod H. I will also call this, for reason that will be clear in a second, a global variant. So this new theory will have some new symmetry, because of course the symmetry that I gauge disappears, is no longer a global symmetry, but then there is a dual symmetry that appears. And since the symmetry is different, there will be a new anomaly. Now, it turns out that if we gauge a discrete symmetry, we are not really introducing new degrees of freedom. There is no photon associated to a discrete group. So this is an operation which is Argy invariant, is reversible, is essentially a topological operation. What it does is just reshuffles the physical information about the theory between twisted and untwisted sectors. So the very same topological information about correlation functions is there. It's just reshuffled in different way among the various sectors of the theory. And so for this reason, I will call all of this theory that I obtain by gauging discrete subgroups global variants. Okay, there's variation on the same theory. But now, so you understand that once you have done this gauging once, maybe you have a new symmetry, you can gauge it again, and you can construct a collection of theories, all of these global variants. They all share the same physical information. It's just reshuffling in a different way. And so the idea now is that you can imagine to take this anomaly TFT, upgrade this TFT from an invertible TQFT to a full-fledged, that means a non-invertible TQFT that has multiple vacua, such that it has this property. There exists one boundary condition in this TQFT, such that if you impose this boundary condition, essentially you go back to the original SPT and you describe the original theory. But any other topological boundary condition effectively describes or corresponds to one of these other global variants. And so the set of topological boundary conditions describes the full set of all these global variants. And studying the various topological boundary conditions, one can study the properties of all of these global variants. Now, of course, if you...
Yes. Sorry, I've got a quick dumb question. It's sometimes said that the possible gauge anomalies in the two-dimensional G gauge theory for finite G are classified by degree 3 group cohomology for finite G in 2 dimensions. Is it possible to draw a link between, I'm looking at that last line, is it possible to see degree 3 group cohomology as classifying, is it possible to compare group cohomology to boundary conditions, I think? Is it possible to make explicit that link between group cohomology?
No, because so that thing that you mentioned, that classifies the anomaly. What we want to, the topological boundary condition corresponds to the possible gaugings. So if you want, corresponds to the parts of the group that are not anomalous, and then you can gauge them, but then maybe you can gauge again. And so it's not obvious how to classify them in terms of some cohomology group. In fact, what you do rather is that you use this SPT phase, if you want this third group cohomology, as a Lagrangian for now, not an SPT, but you make the gauge fields dynamical. So it's a Lagrangian of some TQFT, and then in that TQFT, you study boundary conditions. Which is essentially the module category of this TQFT. In fact, my last point is that anomalies appear as a lack of boundary condition, because if you have an anomaly, you cannot gauge. Now, the existence of this symmetry TFT, if my argument was not convincing, can also be derived from string theory. In fact, this was noticed by Witten long ago. We can take our favorite example, which is in ADS-CFT, which is four-dimensional SUN n equal 4 Siberian mills, dual to type 2B string theory on ADS5 cross S5. We go to low energies, so we are in supergravity. We go at even lower momenta. So at very low momenta, we can drop the kinetic terms, and we only keep the topological term, which is this term here. And now, since we have an S5, we can do the compactification of an S5, and we end up with just a topological term in 5 dimensions. The fact that this is ADS at this point is not very important, because anyway, this is topological, does not depend on the metric. But what is this? Well, this is some sort of Chern-Simons theory, right? It's some BDC. It's also called a BF theory. And in fact, this is equivalent to 5-dimensional two-form ZN gauge theory. So we end up at very low energies with just a topological theory. This is some topological sector of the theory. And then Witten observed that we need to specify boundary conditions for this topological sector, because we are in gravity, and we always have to specify boundary conditions. And depending on the boundary conditions that we choose, we can select what is the global structure of the gauge group of the theory. So the algebra is SUN, but what is the group? So for instance, if we have, let me call them electric topological boundary conditions. So we have Dirichlet boundary condition for B, then we are describing the group SUN. But if we set Dirichlet boundary condition for C, then we are describing PSUN, which is SUN mod ZN. And then there are other boundary conditions that one can consider, and all possible global forms of this algebra can be described in holography. Now, it turns out that these various variants, in fact, are related by gauging, because in SUN, there is an electric one-form symmetry, which is ZN, and if you gauge it, you precisely go to the PSUN theory. So these are precisely global variants of the very same gauge theory, and they are described by topological boundary conditions of some five-dimensional TQFT, which is the one written here.
So here's another quick dumb question. Is it possible to see how to encode discrete theta angles in this language? This is probably well known, but I've just never quite understood this point. So for SUN mod ZN, there should be, oh gee, in 4 dimensions, I'd have to think for a while.
Yes, absolutely, yes. So is this number here that I call 0 means that there is no theta angle, but then if you send theta to theta plus 2 pi, you can say that there is some topological theta angle. So here I will write 1. And this corresponds to boundary conditions which are mixed. For instance, you can set the Dirichlet boundary condition for B2 plus C2 or for B2 plus 2C2. And in fact, there are in total n of these twisted boundary conditions.
I see.
And then the case of SO and SP has been studied by Bergman with somebody else. So all these cases have been studied and everything works out. Okay, so it turns out that the Symmetry TFT encodes a lot of information about the symmetry. We can say that encodes all the rigid structure about the symmetry of a quantum field theory, all the structure that is RG invariant. So the structure of the symmetry, the representations, the anomalies, all the structure which is RG invariant. So yes. Now it turns out that, so I will describe how to extract this information more in detail in a moment. However, let me say that so far this framework of the Symmetry TFT has been applied mainly to the case of finite symmetries. And in fact, also the corresponding mathematical framework, which is the one of category theory, is much better established in the case of topological field theories with a finite number of simple objects. So semi-simple, for instance, modular tensor categories, or depending on the dimensionality where we are. And so the goal of this talk will be to try to construct this for continuous symmetries. And of course, mine will be a physics approach, and it will be very nice to see whether a more rigorous mathematical approach can be constructed as well. Of course, there is work in the mathematic theory, in the mathematical literature about non-semi-simple categories, but the amount of work is much less, and I would say that is an active topic of current research. So here is the plan of my talk. I will first describe what is the basics of this Symmetry TFT to convince you that it is a useful gadget. Then I will tell you what is our proposal for the Symmetry TFT of continuous symmetries. Will be a BF theory, but in which, instead of using standard U1 gauge field, we will use R gauge fields. So gauge fields in which the gauge group is R, as opposed to U1. Then I will tell you about, so I described that if you gauge a discrete symmetry, you are not really introducing new degrees of freedom, but of course we are also interested in engaging U1s. Now this is a non-topological manipulation now because it introduces new degrees of freedom, so I will describe how it fits into this framework, and then along the way I will have various examples depending on time. Of course I want to discuss chiral anomalies in even dimensions. This is a very standard example. And then an example which is very nice is the one of the non-invertible Q mod Z axial symmetry with an ABJ anomaly in 4 dimensions that has been in the last few years discussed in the literature. And then at the end, I will say a few words about the non-Abelian case. Okay, any other question so far on the general philosophy?
All good so far.
Okay, very good. So, so what is this Symmetry TFT? So here is the setup. So the setup is that we take our physical quantum field theory that we start with. As I described in this physical quantum field theory is coupled to the topological theory that I call the Symmetry TFT, In this most simple examples, there is a symmetry for this physical quantum field theory. You couple this symmetry to background fields. You extend these background fields in the bulk, as you would do in anomaly inflow, but then you make them dynamical using the SPT phase as a Lagrangian, and this produces some non-trivial TQFT. But then, in order to keep the dimensionality of the system the same, you also put a topological boundary condition on a parallel copy of your spacetime. So there is a sort of slab, and really the size of the slab doesn't matter because in the middle you have a topological theory. Now, the topological boundary conditions that you put on this topological boundary dictate, because in the bulk you have various topological operators, and the topological boundary conditions essentially dictate which bulk operators can end on the boundary. So in this picture will be the green operators. Essentially, you specify some Dirichlet boundary conditions. So you say which operator can end here. And you can think that these operators are trivialized on the boundary because instead of ending on the boundary, you can think that they continue on the boundary. And since they are not drawn, it means that they are transparent. Okay, they are like the identity operator. They are trivialized there. There is, in fact, another way in which you can think about topological boundary conditions, which is in terms of gauging. Because you can think of this boundary as an interface between your topological quantum field theory and a TQFT in which you have gauged a maximal symmetry such that this TQFT becomes completely trivial. And so here on this side, you can say that there is nothing, it's just empty. And when you perform this gauging, so first of all, you have to figure out a non-anomalous set, a non-anomalous symmetry that you gauge. Moreover, if you want this symmetry to render the TQFT trivial, what you gauge must be maximal. And so this leads, at least for abelian theories, which is what I will describe in most of this talk, to the concept of a Lagrangian algebra. This is a maximal set of mutually local, or if you want trivially braiding operators that you gauge on this side, and so the theory on this side is trivial, and so this is a boundary condition as opposed to an interface, a standard interface. Now, after doing this, you have other operators in your theory, which are red in this picture. And you can move this operator on the boundary. These red operators are not trivialized. And so if you take the bulk operators modulo the one that you trivialize, which is the Lagrangian algebra, this gives you the topological symmetry defect of the boundary theory. These operators are topological because they live in a topological boundary, and they represent the symmetry defect of your physical quantum field theory. So in this way, you reproduce what is the symmetry group. Besides, you can take these red operators, you can fuse them in the bulk, because you know what your topological quantum field theory is. And then if you project, you can infer what is the fusion on the boundary. And in this way, you reconstruct the structure of the symmetry. So this symmetry TFT, you can recover the structure of the symmetry in each global variant, which is specified by a topological boundary condition. Now, in fact, if you go back to these green operators that end on the boundary, they also must end somewhere else. So they have to end also on the physical quantum field theory. Now, this end is not topological, okay, because here this theory is not topological. So these operators represent the physical operator in the theory, which are charged. And so essentially the set of charges is precisely the Lagrangian algebra. So we can think of this Lagrangian algebra as the set of charges in the theory, more generally as a representation. And so if you want, finally, going back to what is an anomaly, so it is clear that anomaly from the abstract point of view should correspond to some phases that one produces when you have topological operators in the bulk and you cross them. These should produce some phases. However, from a more lowbrow point of view, well, we can think of them, as I already said, as a sort of lack of boundary conditions. Of course, this is an incomplete description, but as we'll see in the examples that I will bring, they will precisely appear as a lack of boundary conditions. Once again, this is not a mathematically well-defined. One should give a more rigorous definition, but okay, so far this is what we will do. Is this picture clear?
Yeah.
Okay. So my proposal for the symmetry TFT of U1 symmetries will be BF theory. So I think that it will be useful to first describe the standard BF theories that are mostly described in the literature for the case of discrete symmetry, such that you understand what is the new ingredient when we go from discrete to continuous. So let me describe the standard BF theory description of a ZN P-form symmetry. P-form, sorry, gauge theory in D+1 dimensions. So once again, D is the dimension of the physical theory in the boundary, and the bulk is D+1 dimensional. In fact, this theory is the one that I already described in ADS5. So here is the Lagrangian. There are two U1 gauge fields that can have different degrees. So one is degree P and the other D minus P. And if you call dA as the field strength, you can call it F. So from here, the name BF theory, because B is a potential and F is a field strength. Yes, so in this description, B and A are U1 gauge fields. So in particular, there are both small and large gauge transformations. And in particular, if you want invariance under large gauge transformation, here in front, there must be an integer that we call n. So now what can we say about this theory? So first of all, we have a Dirac quantization condition. This is just valid off shell, so the fluxes are quantized. Then we go on shell. So on shell, first of all, the equations of motion tell us that A and B are flat. So in particular, we can use them to construct some Wilson surfaces. Okay, we integrate these potentials, and because of this condition, these are topological operators. Besides, we also have to do a sum over fluxes because these are potentials. These are not globally defined forms. So on shell, these Wilson surfaces are constrained, okay, by this n. And so, okay, we construct these operators. However, there are two effects. So first of all, because of large gauge transformations of A and B, this alpha and beta must be quantized. They must be integers. Otherwise, it is not invariant under large gauge transformations. Besides, since these integrals on shell are constrained, there are identifications. So if you shift alpha by n, you obtain the same operator on shell. And so because of that, really, these alpha and beta are integers that take a value in Zn. Okay, so these are the topological operators on this theory, and I call them U and W because they have different dimensionality. Okay, this is integrated on a D minus P surface, and this is integrated on a P surface. And they have a canonical braiding among themselves. Okay, so this is the theory. In fact, this identifies the theory as Zn P-form gauge theory. And now let's discuss topological boundary conditions. So essentially, we have to specify a maximal set of mutually local operators. So for instance, we can choose all the W's. You see the braiding is between a W and a U, but the W's are mutually local. They are mutually transparent. So we can choose all the W's. We can choose that they can terminate on the boundary. They form the Lagrangian algebra. So on the other hand, what are the defects that can lie on the boundary, being non-trivial? Then they are the U. But in fact, they are labeled by elements of Zn. And so this gives us a Zn symmetry. And because of their dimensionality, this is a Zn P-1 form symmetry. So this topological boundary condition describes a Zn P-1 form symmetry. In fact, we can think of these topological boundary conditions as Dirichlet boundary conditions for A. You see, A is the field which is integrated integrated in W. So in fact, we are trivializing W on the boundary. And so we can think of this A as the background gauge field for this Zn P-1 form symmetry, and the dimensionalities work. This is a P form. Okay, however, there is also another boundary condition. So we can let the operators U terminate on the boundary, and then the defects Wn are the ones that are non-trivial on the boundary. So this time we have a Zn D minus P-1 form symmetry. So this time we have the Dirichlet boundary condition for B, which is now the background gauge field. So we have two possible symmetries in the theory, and in fact, these two possible symmetries are related by discrete gauging of Zn. If you have a theory with a Zn P-1 form symmetry and you gauge the Zn, this symmetry disappears, but then there is a dual symmetry that appears, which is a D minus P-1 form symmetry, which is again Zn. So we reproduce everything that I described. And okay, depending on n, there might be other boundary conditions. Let me not describe that. So now it comes to our proposal for the case of a U1 symmetry. So we want to describe a U1 symmetry in the boundary theory. And our proposal is that we still write down a BF theory, but in which one of the two fields in an R gauge field. And here I will use a notation in which capital letters are standard U1 gauge field. So A is still a U1, but small letters corresponds to R gauge field. So here will be B. So what is R gauge field? Is a gauge field such that the group is R. And so we still have small gauge transformations, but we do not have large gauge transformations. And so in particular, it is always possible to find a gauge in which this B is a globally defined form. Okay. And so for instance, because of that, the Dirac quantization condition really is just Stokes theorem tells us that the flux is zero. The integral of the flux is zero. Okay, because B is globally defined, and so the integral of differential is zero. Besides, since there is no U1 anymore, we can freely rescale the field B. We cannot do it for A because, again, the fluxes are quantized, but we can do it for B. And so we can always rescale the coefficient here to set it to 1. So there is no longer a meaning of a constant in front of the action. Okay? So our action will be this. Is it clear so far?
Yeah.
Very good. So now what I would like to do is try to describe what are the topological operators in this theory and see what are the topological boundary conditions, and let's see what we get. So because one of the fields is R gauge field, as before, we can do integral, we can construct these Wilson surfaces, but we will get a different set. So let's look at U. So U is the integral of B. Now, we do not have large transformations anymore, so we have less constraints on alpha. So alpha doesn't have to be quantized. It can be a generic real number. We have a continuum of these surfaces U. However, we still have the sum over fluxes of A, or better, of dA. And so because of that, the integral of B is on shell is constrained. And because of that, there is an identification. You can identify alpha with alpha plus 1. And so because of that, you get a U1. So this alpha takes value in U1. On the other hand, let's look at the integrals of A. We still have large gain transformations. So the parameter M is still quantized, is an integer. However, there is no longer a sum over fluxes of B because there are no fluxes of B. And so there are no identifications. And so this M is a generic integer number. So this theory here is a topological field theory with an infinite number of defects, and in fact is a continuum. It has a continuum of defects. Now it is a particularly simple one because it's free, but still, yes. Okay, so then in this theory, we will be able to describe anomalies by adding more terms in the action, but for the moment, let me just proceed with this. So we want to check what happens if we add boundary conditions. Sorry, we want to understand what are the boundary conditions of this theory. So let's do that. The story is similar to before. So we can let the Wm to terminate on the boundary. This will be our Lagrangian algebra. So all the defects U alpha are non-trivial on the boundary, and so they give rise to a U1 P minus 1 form symmetry. And in fact, we can regard AP, which is the field which is integrated in W, as the background gauge field for the U1. However, there is a small subtlety that on shell, we still have the equation of motion that set dA equal to 0. So in this description, we can only describe flat bundles for this U1. This is perhaps one can do better. This description only describes flat bundles. However, as we will see, this will be, for instance, enough to detect chiral anomalies. Perhaps a bit surprisingly, but we will see. We can do something else. We can let the U alpha terminate on the boundary. Then the Wn are the ones which are non-trivial at the boundary. They are parameterized by Z. So what we are describing is a Z D minus P minus 1 form symmetry. This is perhaps a bit strange, but suppose that this was a 0 form symmetry. So suppose that P is actually equal to D minus 1. Then, for instance, this will be the symmetry that you have in band theory, in condensed matter, where you have some scalar with a periodic potential, and you can shift the scalar by integers, and then you have block theorem and all of that. In this case, you have Z 0 form symmetry. So it's a bit unusual, but perhaps not so much. Okay, moreover, let me notice that this example here precisely comes from the previous one if we gauge the U1. However, we have to perform a gauging in which we treat this U1 with a discrete topology. It's not the standard physical gauging. So what do I mean by that? In physical terms, it means that we only sum over flat bundles. So this is not the standard physical process of introducing a photon, and I will come back to that in a moment. For now, it's just some operation that we can perform. It's a sort of discrete gauging of a U1. Okay, we regard U1 as each point is essentially separated from any other point of U1. You put the discrete topology on U1. Okay, so in this sense, we reproduce this framework that the various global variants are related by some topological gauging. Okay. In fact, we can do something else. So we can also choose some of the W's to terminate on the boundary, and then some of the U. We have to do that because we have to construct a maximal set of mutually commuting operators. And then if you do that, let me just be quick on this because of time. You realize a symmetry which is a U1 times some ZB. However, the U1 is smaller than the previous one. Essentially, what you have done is that you have done a gauging of a ZB subgroup of the original U1. So this is also a topological operator, and it is described in this framework. But okay, let me not describe this in full detail. So everything that we expect works here. Is this point clear?
Do I expect a mixed anomaly between U1 and the ZB here?
Yes, very good. Yes. So there should be a mixed anomaly between the two, and there is. So the mixed anomaly is described precisely by this coupling in the bulk, let's see. So I mean, here you don't see it in terms of. I mean, you see it in terms of gauging in the sense that, so if you gauge this ZB, you don't get U1 times the dual ZB. You just get a U1 because the dual ZB is fibered over the U1 in such a way that you get, I mean, you have a Abelian extension and they form a larger U1. If you didn't have the mixed anomaly, you see, if you gauge the ZB, you will get U1 times a dual ZB. But instead, if you gauge the ZB, you get a larger U1. So this is one way to see that this is a mixed anomaly.
I see. Thanks.
Okay, so the very basic example is let's see if we can describe chiral anomalies. So let me consider the case in 2D. So in 2D, the bulk is three-dimensional. So I write down this BF theory in 3D. Both B and A are just standard one-form gauge fields, but B is R and A is U1. And then we add the standard term, the standard Chern-Simons term that describes the chiral anomaly in 2 dimensions. So the standard anomaly inflow term. This K has to be an integer because this is a Chern-Simons term. So now we have to repeat the exercise. So we construct the topological lines. Now, since both A and B are one forms, actually we can construct lines which have two labels, n and alpha. N is an integer, alpha lives on R. Then we construct the braiding. We compute the braiding between these lines. The braiding is modified. You see there is a term here, so it's modified by this extra term. You also compute the spin of these lines. This is the spin in the language of Chern-Simons theory. And the spin is also affected by this K. In mathematical terms, the spin is a quadratic refinement of this pairing. The braiding is a pairing. And so now you can understand what are the identifications because they leave both the braiding and the spin invariant. And there is a small difference if K is even or odd, because when K is even, the theory is bosonic. When K is odd, the theory is fermionic. So there are small differences. So now, just for simplicity, let me focus on the case that K is even. So we are in a bosonic theory. So these are standard Chern-Simons theory as opposed to spin Chern-Simons. So what do we have to do? So we have to identify Lagrangian algebras. So there is an obvious one. We take all the n and we set alpha to 0. If alpha is 0, you see that in this braiding is just you obtain 1. So all these lines are mutually transparent. Now, if you take all the lines modulo the Lagrangian algebra, you have the defect U alpha. Because of the identification, alpha lives in U1. And so we are back to the fact that we are describing a U1 zero-form symmetry in 2D. Okay, so far, no big surprises. However, if you remember before, we were able to also construct the result, another topological boundary condition that arises after the gauging. And now we try to do that, and the point is that we cannot do that. And the reason is that if we try to take all the operators 0 alpha, let me go back here, you see that now they are no longer mutually transparent because there is this extra term controlled by the anomaly. And so even if n is 0, we still have non-trivial braiding. So all these operators are not mutually transparent. And so we cannot form the other Lagrangian algebra 0 alpha. This Lagrangian algebra would have corresponded to the gauging of the U1. And so the fact that there is a lack of a boundary condition precisely appears as a manifestation of the chiral anomaly. And so this might be a bit surprising because I told you that in this framing, we are not able to describe curved bundle. We can only describe flat bundles. And you know, in the chiral anomaly, the chiral anomaly is controlled by the flux, the integral of the flux in 2 dimensions. So perhaps could be a bit surprising that this framing can still describe the chiral anomaly. But after all, it was already noticed that the anomaly of a U1 is uniquely determined by all the discrete subgroups. So in view of this, perhaps this is not so surprising. And anyway, this is what. Now, in fact, there is a little bit more that you can do. So you can ask, for instance, okay, I have a chiral anomaly, but can I at least gauge a discrete subgroup of U1? Is there a discrete subgroup of U1 which is anomaly-free? And in fact, you can try to construct a Lagrangian algebra in which, once again, I don't want to go into the details, but essentially you put some values for alpha and some value for the integer, and you can construct this Lagrangian algebra, and you can study what are the inequivalent boundary defects, and you discover that precisely you get a U1 times ZD. So this corresponds to gauging a ZD subgroup of U1, and it turns out that this can be done only when a 2D divides K. So this should correspond to the fact that when 2D divides K, ZD should be an anomaly-free subgroup of U1. And in fact, you can check this statement with some other methods. This is a true statement. So this reproduces standard expectations. Okay. So there is a similar thing that you can do for the chiral anomaly in 4 dimensions. I don't want to go into the details because of lack of time, but essentially you add, so now we are in 5 dimensions, you add the standard Chern-Simons term in 5 dimensions. The novelty here is that the operators W are lines, the operators U are surfaces, and so if you want to well, essentially, when you define what is a Lagrangian algebra, you define the Lagrangian algebra as a set of operators that are mutually transparent. You should not just look at braiding. There is another observable that should be taken into account, and this is the triple linking number. So if you have 3 surfaces, you can construct a topological invariant in this way. You take 2 of the surfaces, you intersect them. Generically, the intersection is a line, and then you compute the linking between this line and the third 3 surface. You can prove that this is independent of the order of the objects. So this is a triple linking number. And so among the observables, you should include both the braiding between lines and 3 surfaces, but also this triple linking number. And so you should define a Lagrangian algebra as a maximal set of topological operators that are mutually transparent with respect to both observables. And if you do that, you reproduce the same statement. So there is a topological boundary conditions corresponds to the U1. There is no boundary condition or Lagrangian algebra that corresponds to gauging the whole U1, and this is because of this K, essentially for this contribution to the triple linking. However, when 3D divides K, ZD is anomaly free and can be gauged. Okay, is this, I understand that I went quickly through this example, but is this the main idea clear?
Yeah.
Okay. So now I described discrete gauging, but of course, from the physical point of view, we also want to gauge a U1 in the standard physical sense, not just this U1 with a discrete topology. However, as I described before, when we gauge a U1 symmetry, this introduces some new degrees of freedom. There is a dynamical photon. So this should not correspond to a topological manipulation. This operation should not correspond to finding a new boundary condition, okay, at least in our framework. However, it is still a controlled operation, and so we might still expect that, so first of all, we should expect that when we gauge a U1, there should be a new, so we are not identifying a different boundary condition in the same TQFT. We should expect that we have a new TQFT, but we might hope that this is still there is a controlled way to generate the new TQFT from the old TQFT without knowing about all the details of the quantum field theory, just knowing about the structure of the symmetry. And so this is what we try to do. And so the strategy that we use is the following. Let me just try to convey the main idea. So we start with the symmetry TFT of the original theory. Let me call it a matter theory. Okay, this is still the TFT that describes the original theory with U1 symmetry. Then we introduce a free photon. A free photon has 2 symmetry. There is an electric one-phone symmetry described by this piece. There is a magnetic D-3 symmetry which is described by this term here. And then there is a mixed anomaly between the electric and the magnetic symmetries, which is described by this term here. And now we have to couple the two systems. And so we try to write down a term that describes this coupling. And it turns out that this term precisely does the job. So, I mean, if you have questions afterward, I can describe why this term does the job. But so you add this term here. So now you definitely have a new theory. It looks complicated, but it is still free. And essentially, you can regard some gauge field as a Lagrange multiplier. You integrate it out, you play a little bit, and at the end of the day, this collapses to something much simpler, which is what is written here. And we can understand this process in a very simple way, which is the following. So if you want, this is an algorithm. So you take the original U1 gauge field and you substitute its flux with a potential which is R-valued. And on the other hand, you take the R-valued potential and you substitute it with the differential of a U1 potential. So sorry, this F is a potential, it's not a field strength. Perhaps this is a bad letter. So this is a simple argument. Essentially, you exchange the field strength of a U1 by a R potential, and then R potential by the field strength of a U1 gauge, of a U1 potential. Okay, and so we claim that this algorithm produces the symmetry TFT of the theory that you obtain after gauging. Okay, before giving you one example, let me make an observation. For us is an observation. So as I described, so when you gauge this photon, you really have to change the TQFT. And this TQFT lives in one dimension more. However, it turns out that the various TQFTs that you can obtain by gauging photons can be obtained as boundary theories for a master TQFT that lives now in D+2 dimensions. So you have to go in even one dimension more. And this TQFT is constructed essentially with the anomaly polynomial. So because of a lack of better creativity, we call it anomaly polynomial TQFT. So essentially, you write down a TQFT using a BF term in which both fields are R-valued. You add the anomaly polynomial. And then if you take this TQFT that now lives in 2 dimension more, so if we start in 2, now we are in 4, and you study topological boundary conditions, you discover that on topological boundaries, there are some edge modes that live there. And there are topological edge modes. And these topological edge modes precisely corresponds to the various TQFTs that you obtain by gauging photons. So by the procedure that I described before. So I will not go into further details once again because of lack of time. Just let me. So is the idea clear? Otherwise, I can try to rephrase it again.
Yeah.
All right. So yeah. So let me just jump one example. And the example that I want to describe is this 4-dimensional non-invertible axial symmetry with ABJ anomaly. So the story is the following. Take QED, standard QED in 4 dimensions. So there is one Dirac fermion, and there is a photon, okay? Standard QED. There is an axial symmetry, U1A. However, this symmetry is an ABJ anomaly. Now, the standard law, the standard statement that has always been made is that because of this ABJ anomaly, the symmetry exists classically, but is destroyed in the quantum theory, and there is no remnant of this symmetry in the quantum theory. However, what has been recently noticed that this claim is actually not true. There is a subgroup of this symmetry that survives. Well, in the literature, the claim is that this subgroup is a rational subgroup, although there is some work in progress by some other group claiming otherwise. But okay, the claim in the literature is that there is a Q mod Z, and this survives as a non-invertible symmetry. So it's a symmetry that doesn't have the standard multiplication rule of a group, it is generalized in some way. So what we would like to do is to construct the symmetry TFT for this strange beast. Okay. And the way to do that at this point is to exploit the trick that I described. So we start with a free Dirac fermion, for which we can write down the symmetry TFT, and then we use this algorithm to gauge the U1. So I start with a single Dirac fermion. A Dirac fermion has a vector-like symmetry and an axial symmetry. So I can write down a 5-dimensional symmetry TFT for these two groups. So there will be some factor for the first U1, and is there a question?
No.
Okay. And so there will be some 2 gauge fields for the first U1, 2 gauge field for the second U1, and then there will be some terms that describes the Toft anomaly. There is an axial vector-vector anomaly, and there is an axial Toft anomaly. Then, so I've not written this action here, sorry. But then we implement the gauging of the vector-like, because we introduce a photon, we go to QED. So we do this change, this transformation that I described. If there were some fields C and V, we do this transformation and we get something new. And so this is what we get, okay? So this A and B come from the axial symmetry. This F and G come from the gauging of the U1 vector. And this corresponds to the axial vector-vector after the transformation, and this corresponds to the axial. So, okay, so our proposal is that this object here, that now is an interacting topological quantum field theory, is the symmetry TFT for this non-invertible symmetry. And so one can try to check this statement. And what happens in this theory is that if you look at the equations of motion, B3 is no longer flat. Its differential is given by F2, wedge F2. So if you try to construct a 3-dimensional operator as the integral of B3, usually this operator should correspond, once you push it on the boundary, to a zero-form symmetry. In fact, it should correspond to the axial symmetry. However, this is no longer topological because of this fact. So you can try to correct this by writing something else, but then this is not really a tree surface. This is the boundary of a 4-dimensional disk. And so this becomes a sort of trivial operator. However, you essentially repeat the argument that has been given in the boundary in this theory to argue that this survives as a non-invertible symmetry. So instead of adding this disk, what you do is that on the 3-dimensional surface, you add a quantum Hall state. It's some 3-dimensional TQFT that in the literature has a name. It's called AQP. In the simplest case, this is just a U1 Chern-Simons theory. This theory here is coupled to F2 because this theory is an anomaly, so it can be coupled to some background gauge field. And the anomaly precisely has an anomaly inflow term that reproduces this term here. And so when you put together the two things, this integral of B3, but also the partition function of this anomalous theory, then the composition of the two is topological. Essentially because the non-closeness of B3 cancel with the fact that this A is an anomaly. And this anomaly is coupled to F2. So now this operator is topological. So you can construct this object here. However, this trick only works if this number alpha is a rational number, because you need this P and Q to be fed to this quantum Hall state, and this quantum Hall state exists only when Q and P are integers. Essentially, this is the reason why this only exists for a rational subgroup of U1. And now the consequence of this is that if you do the fusion of this U, since this U contains two terms, there is this integral of B3, but there's also this quantum Hall state. Really, you have both to sum. So this U tilde is simple because these are integrals, so you just sum the coefficients. However, you also have to fuse these quantum Hall states. And when you do that, you get some extra prefactors, some extra topological quantum field theories. And so you get these fusion rules that are decorated. You see here, you don't have a number. You don't have something like 1. This would be the standard group law. You have the coefficients are decorated by topological quantum field theories. So for this reason, this is not a standard group, but is a non-invertible symmetry. Okay, so once again, I'm out of time, so let me jump ahead, and if you have questions afterwards, I will be happy to explain more in details. I think I'm out of time, so I will probably have to skip unless you ask me about the non-Abelian case. So let me jump to the conclusions. So what I described is a proposal for the symmetry TFT of U1 symmetries. And in fact, there is also a proposal for the non-Abelian case. This is a BF theory in which you have to use some unusual objects. These are R-gauge fields, and they give rise to a continuum of topological operators. And these are some topological field theories that have not been studied much, even in the mathematical literature. So these are interesting objects. And we also described some action on these TQFTs, some map between one TQFT to another one that is supposed to describe the gauging of a photon. Now, there are lots of questions that, at least for me, are interesting. So first of all, one would like to use these gadgets. One could ask, okay, is this useful for something? Of course, we understand U1 symmetries very well. But if we are in more complicated situations in which there is a mix of continuous and discrete symmetries, then these gadgets become useful just from a practical point of view. Also, if you have some non-Lagrangian theories, then maybe it's not so obvious to identify symmetries, and having at hand these symmetry TFTs, maybe derived from string theories, is something that is very useful. I think that these TQFTs might also be interesting objects on their own. So it would be interesting to study the quantum theory of these BF theories, like can we compute partition function not just in this slab setup, but more generally on compact manifolds? Are they interesting theories? And in fact, it seems that they are related to some TQFTs that are obtained by twisting supersymmetric theories. They have similar character. And finally, the non-Abelian case is also quite interesting. There are a lot of cute things that one can do with this non-Abelian theory, and for sure it deserves more study. But I've not introduced it, so okay. And yes, so that's it. So thank you very much for your attention, and sorry for going over time.
Thank you. Any questions?
I've got a quick vague question. The RBF theory is, by chance, that's something like a large, should I think of that as a large K limit of an ordinary level K U1 BF theory? Is there any sort of relationship like that?
I mean, morally, yes, it should be. In the sense that, yes, you can think that you have the U1 and you look for a Zn subgroup of it. And when n is larger and larger, you have better refinement on it, of it. So I guess, yes, we can think of it in those terms.
Just curious.
Yeah, so, I mean, I've not tried it. It's possible that you can try to do some manipulations in which you write the standard action for Zn gauge theory, and maybe you do some manipulations and you see that you can write it as a, I mean, in the limit, because, yeah, we can think of it as the limit n goes to infinity, but you can ask, what is the end point of this limit? It's not immediately obvious, but it's possible that maybe with some manipulation you can see that, because, I mean, in some sense, an R-gauge fields could be written down as a U1 gauge field in which you put a Lagrange multiplier for the flux.
Yeah. Yeah.
I mean, it's not a Lagrange multiplier for the field strength. The field strength is not zero. It's just the integral of the field strength.
Exactly. Something like a U1 gauge theory in which you're not allowed to have instantons, something
Yes.
like that, something like that.
So it's possible that perhaps if you write in terms of Lagrange multi, I haven't thought about it, but maybe with some manipulation, you can see that it's equivalent to the n to infinity limit of the n-gauge theory. But
Okay. Let me add, I thought it was a really nice talk. I'm also gonna have to leave in a couple minutes to get to another meeting in another building. But if I have to leave before everything's over, it's not a reflection of the talk, which was extremely interesting. So thank you for
Thanks.
speaking.
Any question? Any other question? Can you say a little bit about the non-Abelian case?
yes, so what about the non-Abelian case? So our proposal is to use a theory that in fact was written by Horowitz a long time ago in '89. He literally wrote down this theory. Of course, he didn't have this application in mind. He has application to some to describe gravity. But okay, so here is the theory. So what is this theory? So first of all, we expect that the non-Abelian case can only be done for a zero-form symmetry. So we already know that higher form symmetries are necessarily abelian because the corresponding operators, because of dimensional reasons, must commute when you fuse them. So what we'll have is a standard non-Abelian gauge field. And so we choose, so this will be a standard gauge field for Lie group G. And then we can construct the non-Abelian field strength. So F is the non-Abelian field strength. What about the other guy? The other guy should be R gauge field. Really what this is a collection of R gauge field. So these are D-1 forms. They have small, not large gauge transformations, but besides, they form the adjoint representation of G. So in other words, here there are two gauge transformations. There are the gauge transformation of G, which is a group. And besides, there are small gauge transformation of this little b that can, so, okay, these are written here. So the G gauge transformations act on A as a non-Abelian connection, and they act on B just by rotation. So B is in the adjoint. On the other hand, we can also shift this B by a parameter lambda. However, this D is a covariant derivative, covariant with respect to A. So this lambda is a globally defined section of an adjoint bundle defined by A. So in this sense, this B is a R gauge field. And you can write down this action. This point is very natural. It turns out that this is gauge invariant. The equations of motion tells you that F is flat. So this is precisely what the BF theory does. It tells you that F is flat. And it also tells you that B is flat with respect to this covariant derivative with respect to A. And then, okay, you construct topological operators. So what can you do? So first of all, you can construct Wilson lines. So you take A and you construct the standard Wilson lines. So they are labeled by representations of G. So you have line operators. Oh, bye, Eric. Thank you very much. It was nice
Good to see you again.
So you have line operators labeled by representations of G. Next, in BF theory, what you would do would be integrals of B. As far as I can tell, looking to the literature, it's not known how to construct a gauge invariant operator by integrating B. Essentially because B rotates pointwise with U. So I don't know how to construct integrals of B. However, you can construct Guco-Witten operators, which have the same dimensionality as an integral of B would have. Because, yes, so the integral of B will be on a surface of dimension D-1. So this will be codimension 2. And the Guco-Witten operator is an operator of codimension 2. What is a Guco-Witten operator? Essentially, you say, let me take a surface, And let me impose that on the orthogonal, so if I go orthogonally, I am on a two plane, and as I go around the surface on a two plane, I impose that the flat connection, that there is an holonomy for A, and this holonomy is an element G. Now, when you do a gauge transformation, this holonomy is not invariant, it transforms, and there is a joint action on it. And so really this Google-Witten operator is labeled by a conjugacy class of elements of the group. And so you have codimension 2 operators, which are labeled by conjugacy classes of G. Yes, so these are the topological operators in the theory. In fact, it turns out that you can do a little bit more. This is not written in the literature. There are also some codimension 1 operators that you can construct. Essentially, you freeze on these codimension 1 operators your gauge transformation, and you impose that through this surface, which is now a sort of domain wall, you glue fields with an element of G. And it turns out that these surfaces can be open. So these are topological operators, but are endable operators. These are operators on which you can cut a hole. And it turns out that what lives in the end point of these holes is more really a Google-Witten operators, but which is labeled not by a conjugacy class, but an element of G. So in other words, you can do a little bit better. You can construct a sort of Google-Witten operators, which are labeled not by a conjugacy class, but by a very element of G. The price to pay is that this needs to live at the boundary of a disk, and this disk is this sort of domain wall that I described.
Thank you very much for that explanation.
Yes, so yes, then I mean you can understand that if you have this theory in the bulk, you can impose boundary conditions in which the lines can end on the boundary, and then since the lines are labeled by representations, these lines describe local operators. The end point of a line is a point, so this would be a local operator that transforms some representation R. And then, okay, if you just have this action, this has to be understood. I mean, it's one of the things that would be nice to understand, but one expects that there are some other topological boundary condition that corresponds to the gauging with discrete topology, this non-Abelian group G. But on the other hand, if you add something that corresponds to the chiral anomaly, then this should prevent these other topological boundary conditions. But okay, these are expectations.
I see. Yeah, that's very interesting. Thank you. Thanks. Yeah, I have one more question. So in this continuum symmetry setup, how should I think of the partition function of this slab theory reproduce the boundary theory's partition function? Because it seems like now I'm summing over infinite many gauge field profile. Like, should I introduce any regulator? I mean, because, you know, in the finite symmetry case, right? You consider a slab, then the partition function of this slab, when you're shrinking it, reproduce the partition function of the boundary theory. I mean, the boundary absolute QFT. But in this case, it seems like I have infinitely many gauge field profile to sum over.
Yeah,
It's
so...
a problem,
no.
it's yeah.
Go ahead, sorry, I didn't want to interrupt.
Yeah, sure. Then, yeah, I'm just wondering, do I need to introduce some regulator to make sense of this partition function reproduce as in the finite case? Or it's just still some open question we don't know yet? Yes,
so okay, so let's go back to this. So the way in which the symmetry TFT is used in this business is with this picture, right? So you always use a slab. So you have very peculiar geometries. And what in this, so if you want, this is not holography, in the sense that it's not true that the partition function of the symmetry TFT reproduces the partition function of the physical theory. The physical theory has a very complicated partition function that in general you're not able to compute. I mean, if it's strongly coupled, right? The symmetry TFT only describes the structure of the symmetry. And if you do a gauging of a discrete symmetry, or even a continuous symmetry, but with discrete topology in the boundary theory, essentially how to sum sectors of the physical theory to reconstruct the full topological, the full partition function. But it is not true that the partition function of the bulk theory reproduces the partition function of the boundary theory. Now, in this particular slab setup, essentially you never have to, so essentially you don't have topology in the slab. So you never have some non-contractible cycle in the slab that requires you to sum over all the states that are created by putting operators in these non-contractible cycles. So if you use the symmetry TFT in this particular setup for the purpose of describing the symmetry, I think that you never run into this problem over summing an infinite number of states. However, you might ask, okay, let me take this theory and let me forget this symmetry TFT story and let me just try to put it on a torus or some other manifold that maybe has some internal topology.
Right, yeah, right.
And that is less clear. So this is something that, okay, we are trying to explore, but that is less clear because naively you would say, okay, now, for instance, if I have a torus, I can put lines in the middle of, if I have a handle body or a torus, if I have an infinite number of operators that create an infinite number of states. And so now you need to regulate your theory. If you're just counting the states, you get infinite. In your path integral, you can use some regulator to make these partition functions finite, but then some other partition functions will be zero. Essentially, if you want to TFT to satisfy gluing, some partition function will be zero, which perhaps not super nice, but okay, this is what you have to do. So and you can introduce these regulators.
I see.
In particular, let me mention that something that you can do is to try to use these theories for holography. So now it's a different story. You can say, okay, let me take these TQFTs, let me put a boundary, but let me put not topological, but non-topological boundary condition, for instance, conformal boundary conditions. Then you can try to treat this as an holographic description of something. In particular, you can try to compute the partition function in the bulk and claiming and ask whether this is the partition function of some boundary theory.
Mm-hmm.
And it turns out that, once again, this is some work in progress that I have with some students. And it turns out that if you do that, you discover that these are holographically dual to Goldstone bosons. So some very simple theories. It's not a... Yeah, I mean, it's a very simple theory. Essentially, they are almost free theories. But okay, they're not completely trivial. In particular, you can have some Goldstone bosons with WCW terms, something like that.
I see, okay.
But you have to change your setup. So if you want to do that, because a Goldstone boson is not topological, so you need to put some non-topological boundary conditions.
Yeah, I understand. Now it becomes something more like the Chern-Simons WW dual setup,
Yeah.
I guess. Yeah,
Yes, exactly. Yes.
Thanks. Okay, let's start recording. Yeah, let's thank Francesco again. Very